Um, First of all, thanks everyone for joining, and also thanks Anyscale team for hosting these events. Um, I'm Jawei. I'm from Pinterest. I'm a software engineer, and today I'm going to share some of the lessons that we learned from scaling our Great Batch Inference workload on Kubernetes from single nodes to hundreds of nodes. So Pinterest is a platform that's helped people to find like the life they like, they save a pin and then enjoy those like different pictures on the web. And we just passed our 507 million monthly active user last quarter. This is the agenda today. I'm going to talk about the use case that we are doing and the key challenges that we face at the beginning and also in the middle of the job. And with the learnings that we have, and finally, if we have some time, doing some Q&A. So just a bit of the background. Well, what we're trying to do here is doing array batch inference, but before we have an inference, we need to have a model. So we use an internal clip-like architecture. We fine-tune the model using Pinterest internal data set to train the transformer-based image and text encoder. This is like a very simplified version of a model. So going back to array, how we're going to use it is we're going to take this model and then use it to generate the embedding that's can be used for like text to image search or image to text search, or just use it as a, like features for downstream model to do other ML task. So the scale that we're looking at is we're trying to process billions of image, going to use 300 of G5.4x large nodes, which comes with 16 CPU core, 64 gigabytes, and 1 GPUs in each node. And we estimate to finish it within 2 weeks. Below is the pipeline that looks like we have array data set up there, so we can read the data, download the image, do the pre-proc, and then fit into GPU inference, and finally write to the data set. Sounds very naive and straightforward. We also saw that at the beginning. Here are the key challenges that we notice, or we at least we learned throughout the journey. The very first one is, imagine you're running the job for like 2 weeks, and then things happens, like array heads get deleted, or there's application failure, or maybe you're using some internal libraries that your company are using that is kind of flaky. Sometimes retry is not going to work in array side. Array also have some automatic retry for you, but if it's application failure, sometimes you don't know how to do it, so it just fail at the middle. We also face some of the throughput flakiness when we scale up from 1 node to hundreds of nodes. We also facing like out of memory issues. Array have different type of memory. You have object store, you have heap memory. So we have to carefully tune those in the middle of a job. And we also face some of the GPU availability issues, like capacity is always limited. So how do we make sure that users are able to get started, like even with limited GPUs? That's something we need to think about as a platform. And we'll also talk about some of the hidden costs that when you're doing this large scale data processing, sometimes you have to be aware of the data transfer across the AZ. Okay, going first, fault tolerance. Maybe the question we should ask is why do we even need that? Array data is supposed to have some fault tolerance already, right? You have like lineage reconstruction. But in reality, we noticed that application failure can happen, and then the entire job can just stop and then fail in the middle. So other part is like array head is not completely high availability. If you are running as a array job, you know that even if you set up like GCS, fault tolerance stuff, there's no way for you to resume from the previous state of array job and then start from it. You have to make some checkpoint in the middle to allow it to resume. And it's like often overlooked in inference compared to training. In training, we already usually have some like fault tolerance training, but we seldom talk about inference in this case. And our approach is to basically use a virtual epoch way, like we split the data set into unlogical chunks. The reason why we choose this is it's very simple to implement. It's agnostic to any of rate data pipeline implementation. Imagine you're doing some crazy transformation, sampling or shuffle or join within the data set. It can all works out of the box if we're using this approach. We also have a checkpoint actors, which kind of do the metadata management. Whenever one of subset of data set finish, we save some of metadata and then we return from it. If there's value happens, then we can just use that metadata to skip the data set that's being processed. To make it more concrete, imagine we have like a list of file. Here, what we did is we split those file into unlogical chunks, and then we feed those file sequentially into a number of array data pipeline, so that every time when one of the array data pipeline finish, we write it to some metadata, and then we so on and so forth to the end of the data. However, there's a trade-off, because in general, it's not recommended to split your array data into lists of data, because there will be some kind of like breakpoint. You pretty much set a breakpoint in the middle of a array data pipeline. You have to wait until the array data set to be recreated. And sometimes it can cause your GPUs to be idle. So at the right-hand side, there's below there's a graph. At the left-hand side, you can see that when we have virtual epoch set up, the GPU utilization will have some gap in the middle of switching to the next data set. But if you're using just no virtual epoch setup, the GPU utilization is usually very high. So there's a trade-off you need to make. At least we're making here is we trade a little bit of efficiency to redundancy, make sure that we're able to make progress and then checkpoint it, especially for real large scale job. You don't want to spend too much time to recompute again the data that you already processed. And another trade-off is if you look at the array data pipeline, usually you have one actors that loading the model checkpoint, right? You have it to, and this can be memory intensive, especially you need to do it n times. So if you see the diagram here, when we have n equals to 5, you will see there's 5 times of memory peak coming up, because each time when we reconstruct the array data pipeline, we need to go through the actor initialization again. So there's a chance you run into heap out of memory if you're in a limited like resource, like maybe the node itself doesn't have enough memory for you to use. And maybe the most challenging part that we face is the throughput flatness. So a recap, we want to scale from 1 node to 300 nodes, and we're using virtual epochs equals to 100, which roughly doing the checkpoint every 2 to 3 hours. And then if you look at the diagram here, this is kind of like an output rate, or you can see it as a throughput. We notice throughput start to fluctuate or degrades a lot when we enter the next rate data set. We can only finish like 2% of the entire data set at the beginning. So which is like quite not ideal from users. So we have a few hypotheses. The first one we think about is maybe we should just try newer Ray version, because we're on the Ray 2.10 at the moment. There's a lot of stability fix and there's like Ray data improvement out of the box. So we actually did try it and we can improve from 2% to 3%. But as you can see, like it's still not enough, right? So we look closer into other metrics to see like what's happening inside of Ray. And one of the things that stands out is object store. If we look closer into the object store memory along the time, we immediately notice that there's a spill happening even at the beginning of a first virtual epochs. And whenever the split happens, it can drop, the throughput will drop a lot because writing to disk is much like slower compared to writing to memory. And especially you have a lot of data that is waiting for you to process. So there's no room for the intermediate stage like GPU or preprog or whatever the stage in the middle to process those, because there's literally no enough memory for you to place the intermediate data. So this brings up to another hypothesis. Maybe rate data is not doing back pressure good enough. By back pressure, I mean, imagine you have a pipeline, right? If there's a bottleneck in the pipeline, this bottleneck should tell the previous one, hey, stop dumping too much data. Otherwise, I couldn't consume it at all. So we noticed that in our pipeline, especially the output rate was like super for different stage. There's always a spike happening at the beginning of a next data set. And this spike pretty much tells us like one of the stage is dumping a lot of data at the beginning, causing the later stage cannot consume it and cause the entire pipeline to stale and just eventually stop or degrade the throughput lots. So when we look closer into the rate data overview, we notice that our dataset pipeline can pretty much split into following stage. First one is read the parquet. Second is download image, do the preprog. Third is the GPU inference. Fourth is the write parquet. And the speed for those are like read parquet is very fast. A download and preprog is somehow faster than GPU. GPU is the slow ones. And this is like very, like I guess standard way, right? Because you usually want your GPUs to be like the slowest one is the most expensive resource. So it makes sense for it to be the slowest one. But why does it happens like others? So in this scenario, there's actually some chain effect can happen. Imagine the first stage, the read parquet, generate too much data. The second one, which means like image download preprog, will try to catch up. And then while it's catching up, the GPU operator, the GPU inference part cannot catch up fast enough. So it will lead to the entire object store spill again and again. So how do we solve that? It's actually quite straightforward because if we look closer into the rate data pipeline, it already tells us some insights like why are we not fusing those operators together? If we're able to fuse the operator together, which means that the GPU inference actor can now tell the previous stage, hey, I'm not able to consume the data much faster than you produce. So just stop producing those. But if in the past, when we have a separate stage, GPU inference have to tell to hop ahead, telling the read data set, hey, stop reading data set because you're doing too much and I couldn't consume it. So by looking at our users' application code, we noticed that they set a different number of CPUs in the different RAID task or actor. So which make RAID data cannot fuse those operations together. And by just changing that line, we're able to go from left-hand side, the very flatness or not very stable throughput, to the right-hand side. We're able to see like much stable throughput, and the GPU utilization is also high later. So that's great. Next, I'm going to talk about out-of-memory issues that we face when we try this inference, batch inference. So there's two types of memory in RAID. One is the heap memory, another one is object store. So heap memory is like application memory. You use it when you write the code. Object store is like a shared memory across the workers. It's more like a RAID internal stuff. And by default, object store will use 30% of the available memory in the host. Sometimes it may not be, your application may not need that much to be reserved. It's just like recommended by RAID. So what we did is we take a look at our application, we noticed that sometimes there will be some out of memory happening. And if we look closer into the object store consumption, we are not using object store that much at all. So I remember we set something like 35% at the beginning, and then we can actually tune into like 25 or even lower, depending on the actual metrics that you see. Can we do even better? The answer is probably depends on your application, because first, we noticed a very interesting fact that users are not just saving model weights as a checkpoint. They also save the optimizer states as a checkpoint. So if we look closer into the optimizer state, it's like 4 gigabytes already. And in those limited resource, 4 gigabytes may not seem large, but in our case, it's like 8% of the memory can be used on the host. So I guess the takeaway is you have to always make sure that when you load the data or load the model, are you using the most efficient way to do it? Maybe the Ray data itself matrix can tell you a lot of story, but how do we look into that is not as. Our thought is like, maybe we should just vertical scale the machines instead of using G5.4. We should maybe use a larger one so that we have more memory that can share across different actor. Because a lot of time the peak memory may not be always happens at the same time. You can smooth out those memory by just maybe doing some random sleep for each actors, and then those out of memory can happen less. Another thought is maybe you could just use a heterogeneous cluster, like spin out some CPU workers that can be handling those memory intensive work. The final thought is maybe Ray data can support something like a NAND actor. So it can be reused across the Ray data set. Because right now there's, whenever we create a new data set, you have to reinitialize it again. But in our case, it's actually redundant stuff, right? We should able to use if there's already something that we can use. But it's like just kind of like a wish list. We don't have it yet. Just put it here. Other area that we talk about is like GPU availability, right? You usually don't want users to wait on the machines to be ready. So what we use is we use kubeRay, and then we usually recommend users to set up some min max in their Ray cluster. In our case, we say like min to 50, max to 300. So it allows job to make incremental progress, even though there's like not enough resource to be stored as a full scale. Other learning we have is to maximize, because we try to maximize the chance of the job to get valuable resource, GPUs. So we don't limit Ray cluster to be in a certain AZ. But a lot of time in the, especially for public cloud provider, when you are transfer data across AZ, there's a hidden cost. For us, every gigabytes you pay for 0.02 per dollar, which may not seem a lot, but imagine you're processing a lot of data. It can be a huge deal for you. Just do a simple math, like 20 billions of rows, each may have like 60 kilobytes data. 50% of time you're transferred across the AZ because you have so many GPUs across the cluster. You end up paying like 11,000 just for finishing this job. It doesn't include the machine that you pay for it, you just transfer the data. So what we end up doing is we leverage the Ray data execution options code actor locality. We enable that to minimize the data transfer between the nodes, just to save us a lot of money by just, preventing those data transfer. So just to wrap out a bit, with all the optimization we did, using the Ray data operator, using a smaller virtual epoch, because you have to choose the redundancy between efficiency, and then reduce the peak memory consumption in your Ray data pipeline to make it more stable, and then use the kubeRay auto scaling, use the actor locality. We're able to scale from 1 node, about 130 rows per second, to 300 nodes, 37,000 rows per second, which is pretty good. Like we can get almost 96% of scalability. Yeah, just to wrap out a bit, reliability will improve from 2% to able to finish it. And then scalability, we're able to scale it to like consistently higher throughput and than before, and we're able to do like cost reduction just by setting up some of the parameters that Ray provide. Some of the learning, fault tolerance is critical for large scale inference. Throughout the inference, the job failed maybe 2 to 3 times. So it's critical for you to set some checkpoint. Ray data may not always work out of the box. You have to carefully look at the metrics and fine tune your data pipeline. Make sure that you're fusing the operation as much as possible, because sometimes Ray back pressure is not good as you think about. So be aware of some hidden costs like data transfer provide. Always try to use a newer version of library if possible. There are some of the future works. We're also looking into more efficient way to do Ray data checkpoint. Right now we're using virtually, but as you can see, there's a lot of overhead just to create a new data set. And then there's also a lot of memory fluctuation can happen in the middle. We also want to try like larger backfilling jobs to see like if there's a new findings or something that can apply to our current approach. So we want to keep the Ray version up to date, because simply update the Ray version give us a lot of stability wins. Final is we're actively looking into customized Ray data autoscaler. I know in the newer version of Ray, there's an interface for you to write your own autoscaler policy, basically. And we're experiment using back pressure as a matrix to tell if we want to scale it up, or maybe we should just stop it, because there's no reason for you to scale up if you're already hitting some back pressure in the pipeline. I want to thank all the team member from ML training team and also customer from ATG to help this work to be done. And yeah, I'm happy to take some questions if we have. I think first.
Really nice job. You talked about data transfer cost. Did you guys also monitor? You talked about data transfer costs. You guys also monitor which AZs have cheaper GPUs? Do you monitor GPU price?
We don't monitor which AZ have cheaper GPU, because we usually provision a bunch of GPU in a cluster, and those machines are shared by different users. So in that case, some of the AZ may have more. So it's not always guaranteed to have like one AZ have more or another have less. So we try to make sure that data transfer is as much as possible.
And
Yeah.
are you all in one single cloud provider, or are you spread across?
We use AWS. Yeah.
Thanks.
So you've shown some observability figures kind of stuff like the output flows, etc. Is there some ad hoc stuff, or do you have like a built observability tool in your build for debugging your data workloads?
I think it's just the one that Grafana are using. We just have an internal time series database we kind of proxy those metrics into our time series DB, and then there's another internal tool to share that. But it's pretty much just a replica of Grafana. Even if Grafana is down or something like that, we can still use that to troubleshooting.
Hi, I just wanted to understand a little bit more what you were doing for fault tolerance. Specifically, is it the case that one of your inference tasks takes so long that it's worth checkpointing it in the middle of the task, or is it more that you've got a job of many tasks and you risk losing the task that it completed and the job is?
I think it's more about the first case, like because the job itself can take a lot of time to finish. So you want to make sure that if there's anything happens, even if the job doesn't require too much GPU, the time itself is not going to change, right? For users' perspective, they have to wait until this amount of time to finish their job. So if their job is more than like 1 day or two, we usually recommend them to do a checkpoint in maybe 10 hours or just some reasonable number that they feel like it's acceptable.
And it's just like one pass through, so it's LLM is taking up to hours, or I'm just curious to understand what sort of inference job you're doing.
You mean what inference scale or?
Like what, or would you just maybe describe what your job is again?
Oh, our inference job is generating the text and image embedding from a clip-like architecture. But we also do a lot of other like vLLM stuff. This is just one of the use case that we want to talk about, because this is like the largest one that we recently did at Pinterest. For other smaller scale, usually users are optional to use checkpoint. If it's like finished within 1 day, we don't recommend you to do it at all. Yeah.
Okay.
Yeah, it's one gigabyte, like we say about build it. It means like it's about several matches and you merge them into one. So
Yeah, so if we look at the rate data overview, it actually tells you like different stage already, right? So what we did is make sure that these two are mixed into a single one. As you can see, this read target data source is now at the same stage of this pipeline.
so this is achieved by re-comparing or like you chain of code, which is
Oh, it's I think Ray data already have this. Like they have a fuse, like some operation that is allowed to fuse, then they will fuse it as much as possible.
oh
Yeah.
Thank
Oh yeah.
you.
There were the, so response times were faster, so we use scaling it accordingly.
Sorry, I cannot share the.
Yeah, so I just have a question related to network congestion. If there's any network congestion to identify and schedule your tasks accordingly to sort of mitigate network congestion.
I think Ray itself had very good observability. So if you see like a back pressures happening, there's a dashboard for you to take a look. So what we usually do is take a look at if there's any weird or suspicious happens for different metrics. And then if that's the case, we need to look closer into how to reproduce that. And then maybe there's a bug in our code too. Does that answer your question or?
Partly, it's not dynamic schedule, like it identifies something and it automatically schedules the next task on the GPU, which is faster, more responsive. Or maybe there's some big flag that's happening on certain machines. So once you've identified the big flag that's happening on certain machines, it's scheduled accordingly on other ones.
If I understand correctly, Ray data will kind of adjust. If there's like slower one, it will just dispatch to like other normal one. So if there's one GPU's like flagness, I imagine Ray data knows like these actors had a lot of back pressure already, so just not assigned to this one and assigned to a different one. But I think that's a good call.
Do you have to make any special provisions for actioning back pressure? You said that if there is back pressure on GPU, the previous stages can slow down the processing. Is there a distinct setup for it? Or are you using out-of-box feature?
We use out-of-the-box features. The reason why I mentioned is because we simply just fuse the Ray data pipeline to a smaller chunk as much as possible. Maybe the things that you're talking about is more like the future work we're considering, which is make sure that Ray data autoscaler can be more customizable instead of just knowing that we have resource, we can scale it up. Maybe it can be application awareness, like there's a back pressure that's happening in the pipeline, then we should just stop scaling up. Yeah.
So that's kind of wish list, right?
Yeah.
You're up.
Just share my screen. First. Two. Okay, let's see. Two. All right. Can everyone hear me? Cool. Welcome. So before this talk, I changed the title a little bit to better represent what we're gonna talk about. So today I'm gonna talk about larger scale distributed inference with vLLM and Ray. A lot of stuff that I'm gonna cover today is very much inspired by the open source effort that DeepSeek did, and I'm going to talk about the explicit features that we worked with vLLM to essentially ship those into open source ecosystem. A little bit, let me just see. Yeah, okay, I can do this. A little bit bio about myself. I'm an engineering lead on the LLM team at Anyscale. Before Anyscale, I did my PhD at UC Berkeley on the topic of unsupervised reinforcement learning with Peter Abil and Vladimir Stoyanovich. I have worked on Ray for about 3+ years now in different contexts, mostly in RL, post-training, LLMs, inference, and essentially like supervised fine-tuning on LLMs. This talk is kind of outlined this way. I'm going to first cover where Ray is used inside vLLM. I'm going to give a brief intro on the recent effort that we're pushing a lot of Ray native LLM APIs out in the open source ecosystem. I'm going to cover those. And I'm going to do a little bit of tech deep dive on two topics related to DeepSeek effort, specifically prefill decode disaggregation and LLM-aware routing. And then I'm going to talk about the roadmap that is ahead of us and where we are headed to. Cool. So let's start with vLLM first. So vLLM is very like a performant modular LLM inference engine with native Ray support. It's kind of one of the only engines that have native Ray support. Like the way you can use it is that they have like a very user-friendly CLI which you can use to spin up, new models, configure engine settings, and directly get an OpenAI compatible API and query. But it also gives you ability to use their generic primitives and integrate with your like larger scale ecosystem. This is how we kind of use them in their using their generic primitives. There are two places that Ray really is used within the engine itself. The first part is that Ray can be used as the distributed executor backend for model execution. So in vLLM, you can do something vLLM serve, the model and -- distributed executor backend Ray. And what this allows you to do, it essentially allows the engine to have a very fine-grained control over the placement of these workers, distributed workers over your physical hardware. And you can do very easily like a multi-node distributed inference. So if you didn't use Ray, essentially the boundary of like what you can achieve is essentially single node. So for something like pipeline parallelism and like PP2, TP2, your workers are confined to being like a single node. But with Ray distributed backend, you can essentially very easily like place them on different nodes and have like a larger scale deployment. So this is the current way of deploying DeepSeek R1 models. For example, we can use this like Ray backend to do a like 16 GPU single replica deployment, pipeline parallelism 2 and TP8 on an H100 cluster. Another place Ray is used is this DP attention core engine orchestrator. But before we get into that, let me explain a little bit what DP attention is. So this is one of those core ideas that DeepSeek kind of popularized. The idea behind DP attention is like it's data parallelism, but your model at each layer, you're doing data parallelism on the attention layers, but the MOE is still either tensor parallelized or expert parallelized. What this allows you to do is like in an architecture where there is MLA, by adopting this type of deployment and parallelism, you can avoid duplicating KV cache across workers, effectively increasing your throughput that you can achieve across this like number of workers. The way it works is that you actually end up batching, splitting your inputs at the request level instead of at like token level. So you may end up with like, different engines being in different stages of, inference. Some of them might be in pre-fill, some of them might be idle, no batches assigned to them, and some of them may be decoding. And the important part is like, because per layer, you have attention and MOE, there should be a synchronization point. So these data parallel groups are not totally independent of each other. There's like these like layer by layer synchronization point. So there is like a very complex orchestration that needs to happen in terms of like sending requests, synchronizing these guys and like making sure all these like DP workers are getting forward passed in the same way. So now, very recently, like as two weeks ago, essentially we shipped this on vLLM where you can serve a model by setting the data parallel size and setting a backend for it, which is Ray. When you do this, what happens is like, so before I say what happens, this is like how DP parallelism works in vLLM. So vLLM is comprised of two basically parts. One is the front-end server, which is essentially having like the fast API and a client, and it does a lot of pre-processing stuff. And then you have this core engine, which is a constantly running busy loop that is exchanging messages to the front end with this like zero message queue kind of paradigm. Now, when you use Ray, these busy loop core processes turn out are essentially orchestrated via actors. And then there's a very centralized engine core manager, which spins them up, orchestrates them, checks their health. And basically you can have a single click type of deployment. If you don't use Ray, you have to essentially log into every node, set many addresses and stuff, and say this is N of these workers are running locally, a few of them running remotely, and have to carry that mental model and cognitive load all the time. But with Ray, you can have a single click deployment, single command line deployment within vLLM. Now, let's talk a little bit about scaling LLM inference. So vLLM is really focused on single replica deployment. It's great for it. But when it comes to horizontal scaling, you need to still do it around vLLM, right? And it's not supported out of the box with it. And more importantly, this type of multi-model LLM deployment, it becomes much more complex when you have in agentic era, where you have many models with different capabilities that have to be talking to each other in very arbitrary ways. So we want to kind of address this horizontal scaling problem at a different layer. So there are going to be two types of inference when we think about it. One is the type of workloads that was previously talked about at this podium, which was the offline batch jobs. In this type of jobs, your main goal is to have like very high throughput inference in data pipelines. So you can have different stages of inference that are chained together, and your objective is to maximize throughput, end-to-end throughput. And on the online side, you actually care about the latency of each request as well as maximizing throughput overall. So the objective is a little bit different. That gives different optimization opportunities for each one. So we basically introduced like different libraries or extensions of existing libraries for each one. So the way I map it to, you can have like a mental model of how these APIs fit in the existing ecosystem is that at the bottom layer, you have your infrastructure, it could be Kubernetes, VMs like Anyscale. Ray core runs on top of this infrastructure, and we have these verticalized libraries like Ray Data, Ray Serve, Ray Train. Ray, like these APIs that I'm going to talk about, there are two of them for batch offline workloads. We have extended Ray Data APIs, data LLM APIs, which essentially inherit all the nice things about data APIs, but are geared toward LLM use cases. Similarly, for Serve, for online serving, we have extended existing concepts in Ray Serve to make them geared toward LLM applications. Now let's talk about each one individually. So Ray Data, the type of problems Ray Data solves out of the bat is things around auto scaling, load balancing, fault tolerance, support for GPU, large GPU and large models. But the key problem that still exists is that you have to still write a lot of code to really like target them towards LLM applications, right? Things like I need to support continuous batching. I need to disaggregate my tokenizer, detokenizer so that I can maximize my throughput. It's tricky to handle model parallelism like tensor parallelism. So these data LLM APIs are trying to solve this type of problems on top of the existing, foundation, which is the Ray data side. Now, I'm just going to give you some examples of like what user experience looks like on these APIs. So you import something like from Ray data package from the .lm as like a config object. Here I'm doing something for vLLM. In this config class, you can define your model name, your vLLM engine arguments, set up like scaling, concurrency, stuff like that, and then batch size for fault tolerance and stuff like that. And then what happens once you have this config, you can construct these LLM processors, which are essentially multiple stages of data pipeline, just lumped together, where you can apply it onto at any arbitrary stage on your data pipeline, right? You can define pre-processor and post-processor Lambda functions to just have like schema matching between one stage and another. And then you can, apply it. You can read your data set in the same, like using Ray data native APIs. You can apply it. It's a lazy execution. It doesn't execute until you actually either iterate through it or materialize your data set. So Ray data, LLM APIs out of the box support things like continuous batching, load balancing across cluster, model parallelism support, all of this great stuff. Now, on the online side, Ray Serve, the problems that it solves is similar. It's auto scaling, load balancing, model multiplexing, and it simplifies deployment story, like whether it's multi-model or multi-app. But still, you have to do things like LoRa management. If you have like, dynamic LoRa adapter that you want to like serve, you still have to write a lot of code to make it OpenAI compatible. And more importantly, for orchestration model placement, you have to still do that, right? But on the serve side, we kind of address these and then take a config-based approach where you can define a configuration, a lot of knobs to play with, and then that gets mapped to a serve deployment that essentially kind of scales properly and addresses all of those problems. So a code for that would look like similarly, you import some configuration. The configuration, you define your models, model source, scalability, and engine arguments. And then you can import some primitive deployment concepts that are essentially extended on top of existing concepts in Serve. So here I'm importing like LM server, which is essentially a deployment object responsible for running engines and scaling that side. And then LM router, which is the front end for OpenAI compatibility multimodal serving. And then you can have like a Pythonic API throughout and then do a serve run, which essentially deploys your application. So in other words, RayServe LM provides native APIs for serving LMs on RayServe. The problem scope that it solves is like OpenAI compatibility, LoRa management, model parallelism, and stuff like this. You can deploy these settings, these libraries anywhere Ray runs. You can have deployed on Kubernetes, which is as easy as like installing kube-ray operator, instantiating your cluster, and running your serve run command, or on Anyscale, where you can have like Anyscale service deploy and a single YAML file which describes the entire service. Now I'm going to talk about topics more relevant to larger scale inference, disaggregated serving, and LLM-aware load balancing. So disaggregated serving, it's very important for low latency applications and having more predictable SLAs on latency. And when I get to LLM-aware routing, I mostly talk about KV cache-aware routing, but the concept can generalize to other type of LLM-aware routing, like throughput-aware, or like in the context of data parallelism, like data parallel-aware. So let's talk about disaggregated prefill. What is it, first of all, right? So this figure is coming from this serve paper, which essentially showed first time that like why people should care about disaggregated serving. So on the top, you see TTFT, like time to first token, which is a metric for measuring how fast your prefill is. And then TPOT, time per output token, which is a measure of how fast your decode is. If you have an engine that is doing just prefill, that's the orange one, and you can achieve your SLA of 400 millisecond at a very like good high concurrency rate. Similarly, for an engine that is only doing decode, you can do that, achieve your SLA also at a very high concurrency. But when you use an engine that is doing both prefill and decode, because prefill also essentially like interferes with decoding, you lose the optimum of both of them, right? So the idea is we can actually use more resources, but then decouple prefill and decode and gain more essentially efficiency than we lose by multiplying our resources. So the idea is you decouple prefill and decode. You have engines that are doing only prefill and then engines that are doing only decode. And there's a centralized controller which orchestrates how the request is routed between them. And then there is a transfer layer involved, which transfers the KV cache computed on the prefill stage into the decode, so you can essentially continue with decoding. Now, let's talk about how we implemented this in Serve. So in Serve, you have a concept like deployment, which is essentially refers to a unit of scale. So when I have a deployment, I can scale those deployments independently. On the top side, we have like LLM router that I just showed you guys. It's an OpenAI compatible thing. There is this centralized controller, which controls requests going to prefill and decode. And there's prefill and decode deployments. So when a request comes from a client after hitting like PD proxy, it first goes to prefill. Prefill comes back with like a metadata and computed first token. The metadata involves information about like where your KV cache is going to be stored. And then PD proxy forwards that to the decode instance. The decode instance pulls KV cache directly from prefill through a transfer layer, such as Anyscale from NVIDIA. And then as the tokens are getting streamed and decoded, it can stream it back all the way to the client. This happens all within the context of Serve. Masood is blocking the text there, but basically it's similar to the original concept that I mentioned. You can have independent configurations for prefill and decode. and then define essentially, construct their deployments and then separate them into prefill and decode. You bind them to a PD proxy deployment, and then you bind that to the LLM router, and then do a serve run. All in Python, very nice, concise, and it still does the scaling and auto scaling and everything. So the nice thing about this is like it inherits all the nice features of serve out of the box, right? Fault tolerance, load balancing, and auto scaling. So this is a figure of doing this in like practice, right? So here I want to demonstrate that we can independently scale prefill and decode from one another. So this is just a span of 10 minutes, and we are sending a workload where we intentionally flip the workload from being like normal to a prefill heavy workload, and then flip it back to a decode heavy workload. And what we want to show is like prefill deployment can scale independently when it's prefill heavy, and then when you do decode heavy, it scales. It flips the other way around. And this graph shows the number of replicas for each mode. So you can see that at that timestamp, prefill went up, and then it comes back down, and then decode goes back up, right? And during this time, if you monitor our TTFD, we can see that during the time that it became prefill heavy, our TTFD just jumped up, and then after auto scaling comes back down, while your teapot is always like sitting at like a low number around like 15 milliseconds. Now let's talk about LLM load balancing a little bit. I will talk about it in the context of KV cache over request routing. So before that, you need to know what prefix caching is. So prefix caching is this idea of skipping prefill for seen prefixes, which ultimately results in faster time to first token. Very effective in multi-turn context. Just an example, like in a multi-turn conversation, you have like, when you ask your first question, the LLM might come back with like a lot of tokens, right? And then when you want to ask append like the second turn, you have to essentially, recompute prefill for all of these tokens, right? But if it's cached properly, you can avoid that computation and then get a faster time to first token. Now, in a context where you have a lot of replicas, each one having their own prefill prefix caching, the important question is when a request comes in, which replica do you route it to so that you can actually do this KV cache reuse, right? By default, serve uses a power of 2 algorithm, which is essentially about probing 2 replicas and choosing the less busy one based on number of requests. This is a very simple and effective load balancing strategy for workloads that are uniform, meaning that I know that almost all of requests take the same amount of compute and time to complete. But this is not true for like LLMs, and in LLMs, the request routing depends on the content of the request. So the idea is we want to introduce something that is prefix aware. And basically, what we want is to have like a global state that keeps track of a prefix tree, mapping the requests that I've seen so far in form of a radix tree, mapped to the replica that actually processed that request. So during routing a request, you first query this data structure to see which replica has the highest cache hit rate, and use that information to kind of inform the decision of routing for choosing that replica. So some early results of this idea, we tried on shared GPT dataset, real-world ChatGPT conversations on a Qwen model, small Qwen model, but on 4 L4 GPUs. You can kind of roughly see across the board, prefix aware router is better than power of 2 in both time to first token and and teapot, which ultimately reduces your end-to-end latency. The nice thing about this effort is that now we have a new concept in RayServe that allows you to customize your routing strategy. So when you're defining a serve deployment, you can have your custom request routing class that can, incorporate your own desired metrics, make it KV cache aware, throughput aware, any type of function that you want to use. And coming back to like, DeepSeek's kind of architecture, there is a section that talks about different load balancings for P&D. Essentially, this is what we want to incorporate using this API. Ultimately, I think the user experience will look like something like this. When you want to construct the LM deployment, you pass in a kind of a custom class for prefill and decode separately, which allows you to kind of like have different policies for prefill and decode. Because prefill is like compute intensive. It doesn't have to be KV cache aware, but the decode has to be KV cache aware, and it's, the load balancing logic depends on number of decoding tokens in the pipeline. Now, a little bit of kind of as part of the wrap up, I want to say where we are today, what has been released, what is going to be released. So in these vLLM APIs that I talked about has been released since Ray 2.43. So we are right now at 4.6, which is like 3 versions. They have been like already in the Ray ecosystem. The things that are supported right now are like this dynamic LoRa loading, structured output generation, vision language models, auto scaling, and fault tolerance because of serve ID already. There's a lot of like observability layers around LMs, so not just serve, but also like LM specific, like tokens, stuff like that. And then in our benchmarks, we see a very good large linear horizontal scaling up to medium tier concurrencies, like 128 requests per replica. Similarly, it has a very good like streaming performance up to those concurrencies. Now, where the things that are in progress or are getting shipped, I talked about disaggregated serving. The first iteration of this will be released on 2.47. Next, we want to iterate on performance and reliability of this thing. So it's not really production ready. Same thing with custom request routing. The first iteration will be released on 2.47 again. A lot of studies need to be done on like the actual policy for routing and implementing, the prefill decode load balancing separately, and also making it DP attention aware. Yeah, so that's all. If you haven't really used these APIs and you have LM use cases, I think it would be great to hear your feedback and ideas on like where this really works and doesn't work. You can check our Slack, Discourse, or like GitHub if you have any questions. Thanks. Questions?
Yeah, like very great talk. I was just curious if you've done any comparison of, Racer compared to like other LLM control planes, like let's say Case or either with respect to features or like benchmarking.
I think it's coming. So basically, as part of we have to do head-to-head comparisons on each of these metrics that I talked about. One of the angles that Racer has is like it's not like you're not bounded to Kubernetes concepts, like load balancing has like limitations on like how you customize it. There's a lot of effort that are built on top of Kubernetes, like LMD, Dynamo, that are emerging. But yeah, regarding, I think KServe, it was not even on our radar, to be honest. But like, I think the more serious ones that are emerging are like Dynamo, LMD, that we are gonna really compare against. Cool. Got another question? No questions from me.
Similar ones.
Yeah.
The dynamic.
Yeah.
So it's a slightly related question to what you presented, but what kind of workloads are prefill only, where the disaggregation makes a difference? I'm just curious. Like when would it be prefill heavy versus just decode heavy?
Just to be clear, I think like it's not that prefill disaggregation is going to be only useful when you have prefill heavy, right? It's really when you have a varying workload where there's a natural interfere between prefill and decode. You cannot predict, how big your prefill is or how big your decode is. But to answer the other part of the question, which is like, what type of workloads are prefill heavy? Like summarization, RAG, these are like large input context, short output. And then for decode heavy, you have reasoning models that are, generating a bunch of tokens, and then the input may not necessarily be live.
Thank you.
Yeah.
Thank you.
Questions, is that?
Just a quick question. The autoscaler, it happens independently for the pre-flow and the.
Yeah.
workloads?
The key idea there is like we define these as independent deployments, and deployment in serve is a concept that separates scaling unit, and that's why it happens.
And it just works based on metrics and things like that.
Yeah. So I think the default auto scaling is based on metrics like number of requests in the queue and how much you wanna like the target you set for that, and yeah, once it passes that thing, it auto scales. It uses Ray auto scaler to do that.
So regardless of whether I have a pre-filled heavy workload or something more balanced, it should scale pretty.
So the thing is, when you have prefill heavy workload, naturally your prefill is gonna see a lot of more requests on its queue. It's gonna auto scale to resolve those. And then decode it has a separate queue. So that one is controlled with a different signal. Right.
Follow-up question on LLM. So did you see LLM as a competitor or something that is going to sit above what you just shared?
So in some ways, I think it's gonna be competitor. In some ways, not. So LMD is gonna be, it's positioning itself as like Kubernetes native. And Kubernetes has like a lot of like limitations they have to work around, right? Like, they're basically trying to solve those, some of them at Kubernetes level, some of them are not. I think like another aspect of Ray is that it is used in the engine itself. So for multi-node deployment or DP attention, for example, right? It's hard to do it in Kubernetes. Like if you're in the mode of like large distributed inference, like DP or pipeline parallelism, doing it in Kubernetes is going to be a little bit harder. Like, or I don't know, like the concepts don't like really match each other. So what they end up doing is probably like hacking around it or like finding solutions around it, right? But our solution is like Ray native, like in the entire stack. The placement groups is going to be shared. There's going to be one Ray cluster that is aware of everything. And the scheduling can be more optimal, things like this.
So is it accurate to say that for VM deployments, this is a better fit than something?
I think if you end up using KubeRay, you can essentially get around it because you want to have a centralized, essentially like controller that is aware of all the resources in the cluster. And if you do what they're doing, like containerization around it, so for example, P is going to have its own Ray cluster, and then D is going to have its own Ray cluster. And then what happens when you like want to over provision? There's no sharing of resources, right, between the two. But then with KubeRay, you can have one Ray cluster and then use these APIs to kind of share resources across them.
So I think that what you just shared, you had queue-based auto scaling of the underlying infra as well.
Yes.
Okay. And that's what the LLM community is trying to build out.
Yeah, I think still far, but let's see how it plays out.
Thank you.
Yeah.
Okay, great. Well, thank you all for joining.